Great. So, so far we have seen how to make single stage fully differential op amp, and we know how to stabilize this common mode feedback. Any questions on this? I'll assume things are clear. So now to increase the DC gain, now you can put cascodes here and increase it, but it is still a single stage OTA. What is the issue with single stage OTA? Resistive load, it cannot drive. So what is the fix for that? Two stage. So let's see how to make a fully differential two stage OTA. So I'll use this as the first stage. Where is all this? This is the first stage. Now the second stage can be a common source. So here the second stage will be a PMOS input common source or NMOS input common source. PMOS input. Hopefully it is clear now. So I'll draw PMOS common source. So is that all, or I should add something else also? I mean, is this done or? Forget about, I mean, common mode feedback and all, but differential mode circuit, is it done or should I add something also? It's a differential output, right? One output is here. Where is the other output? I should have the same thing here also, right? Should be fully symmetrical. So I should add another common source on this side also. So I'll say both of them are connected to the same voltage. Right. So these are the two outputs, right? This is, let us say, the plus input minus input, and I can define anything. Let's say this is the plus output minus output. Properly symmetrical, fully differential. And now we have to compensate this in the differential mode picture. So what are the two things you know for compensation? Miller and feed forward. Let's do Miller. So to compensate with Miller compensation, what should I do? Should put a where? Across? Output of the first stage. So let us say, I mean, I have two outputs. From each of them I should have this capacitor. From here I'll connect it to the final output, and I'll, let's say, add the zero cancelling resistor also. Same thing I have to do on the other side also. Right? So this kind of compensates the differential mode amplifier. This is the core part of your circuit. This is done. So now tell me, are the common modes here set automatically, or you should do something? You should have common mode feedback for setting the common modes here. Similarly, even the common modes at this output is also not defined. So you should have common mode feedback loops to set the common modes of the first stage as well as the second stage. So I'll just mark it as a block. So let us say you use the CMFB here. It can be anything that we have seen. So it can fix the NMOS current and tune the PMOS current, or vice versa. So I'll just say it's tuning the PMOS current for an example. So now let us see what are the possible options you can use for this CMFB. Right? So let me write it here. This is CMFB 1. So now we have 5 different variants. So tell me, first of all, can I use resistive common mode detector like this, or I should use one of these here? Based on whatever we have seen so far, for the first stage, do you think it is better for me to use a resistive common mode detector like this, or something like this based on MOSFETs? The resistive thingy. Why?
Because there is means output swings will be maximized, so first stage will have better output. Resistive loading will not be a problem for the first stage as long as we are using the second stage.
Oh, is it? I mean, in a two-stage op-amp, what is providing the bulk of the gain? So, which will have the maximum gain? Right? In fact, you might have a cascade in the first stage. The output resistance might be very, very large. So, this becomes problem. So, this with respect to loading, it is good. But he pointed out, what about the output swings? Is that a problem? Or it is okay? I mean, remember that this is a two-stage op-amp. Let me see if I can help you. Two-stage op-amp, and this forms the complete op-amp like this, right? So now I am going to put this in some kind of feedback. Now the final output is going to swing like this, maximum. If so, what can you say about the swings at the first stage output? Yeah, I mean, if I call the gain of the second stage as some A2, what can you comment about the swings at the first stage output? It will be A2 times smaller. So the output of the first stage, the swings might not be so large. Even if you have a gain of 10 from the second stage, the swings here is going to be 10 times smaller. So the output swings are not so much. So you can actually work with any of these. So that's what you should do. You should use any of the variants 3, 4 or 5. Anything is fine. So now remember, I should also give a common mode reference for this so that I know what value I want my output common mode to. So here again, is there any constraint or I can use any value? That is, if I change the output common mode, do you think it affects something else in the circuit or it's okay? It's also connected to the second stage. Now based on your final specifications, you might have decided that my second stage should have a particular GM, some particular current. So let's say this is M5, current here is some, I think I've been using the current to be I6. So ideally, what do I want my output common mode to be? VDD? No. I mean, based on this, VDD minus VSG of M5 at a current of, at what current? So this is what you want your output common mode to be set to. Okay. So you can't arbitrarily choose anything because that is going to finally impact your second stage GM and ID. So which means you have to generate this voltage. How do you think I can generate this voltage and feed it? Remember, this is a reference voltage that you have to feed it to your CMFB. So how can I generate a voltage which is VDD minus VSG5? Huh? Where do you want op-amp here? I mean, the question is simple, right? Let us say I want to generate a bias voltage that is equal to VDD minus VSG5. How can I generate it? I have a PMOS, okay. What do I do then? A2? No, but if I connect it like this, the output common mode as such is not defined, remember. I have to use the CMFB to set this voltage. Now for CMFB to function, I need to feed in a voltage which is this. The question is, how will I generate a voltage which is VDD minus VSG and feed it to my CMFB1? What should I do? Diode? I do this, and what current I'll use here? So this will be an identical copy of M5. I'll call it M5X. Right? That's all, right? This is fine. And again, if you don't want to spend a lot of current in this, you scale down everything. And I mean, see, now you see that the common mode I need here is VDD minus VSG, right? So now based on the variants we have seen, do you think one of the variants might be better here? Or maybe if you don't remember. So let's look at the last variant we saw. Here the output common mode is getting set to VDD minus VSG at some current. So which means if I go and connect this to my second stage now, let me make some space. let us say I use this CMFB and I connect it to my second stage here. My second stage also needs some VDD minus VSG, right? So do you think now can you tell me this is better? And remember, I want the VSGs of this transistor to be same as this transistor. So what will I do? Not size them same. The current densities of all these should be same. I put it as a green dot. So it just means that I use the same length and current densities. Remember that I want VSG to be same, which means the lookup table parameters all should be same. Moment I fix a length and one parameter, everything else is frozen. So I'll choose the length, same length and same current density. So that way the last common mode feedback variant we saw might be easier thing to do. It's not that you should always use it, but it makes be easier. So, and again, I should make sure that the PMOSs all have the same current density. Right? That's something we have seen before also. Cool. So this with that is with CMFB1. Now remember that even for my second stage, the output common mode is not set automatically. I should put some CMFB loop. So for the second stage, so I have to sense the final outputs and set the common mode. So once again, tell me among these two which is better. If I were to use a CMFB for my second stage, tell me if I should choose from the left side column or the right side column. Why? Yeah, output swings are very large because the final output I wanted to swing as high as possible. But what about resistive loading? Yeah, I mean, remember the second stage is not there for giving you a lot of gain. The gain of second stage might be reasonable, like probably 10 or 20. For that small value of gain, you can actually use a larger RCM and make sure that loading is not a problem. That's a practical thing that you can do. The RCM value you need for the second stage might not be impractically large. So that's what I'll have to do. So let me just draw that. So I'll use a resistive common mode detector like this. Okay. And then I'll have to let's see if we can make some space. And I'll compare this with a reference voltage and what might be a reasonable value for my common mode at the output to be. Questions? Where this is? Oh, you put it separately and use it as a bias voltage here, right? I mean, the idea is for my first CMFB, I need to generate this VCM ref 1. And that VCM ref 1 should be VDD minus VSG of M5. Right? So what you have to do is this, you put it separately and go and connect it here. Is fine?
So when you are using that other
there you don't need to do it. Yeah. I mean, because there the reference, I mean, see, the CM only in, I will say, these three, you feed in a separate VCM ref. Yeah, if you use these three, you should do that. If you use the last variant, you don't have to. But if you use the last variant, you have to make sure that the current densities of the PMOS transistors are all same. Only then the VSCs will be equal, then you will be fine.
So you basically need to tweak the lower NMOS.
Which one? VBN. VBN you are not tweaking, right? Remember here the idea is I fix the two currents here and I change the additional current. Right. This is a, you can say, third different kind of approach. Yeah, so now for second stage, what might be a reasonable common mode to have at the output? VDD by 2, you want symmetric swings on both positive and negative. So this you can maybe keep it at VDD by 2, but not always necessary that it should be VDD by 2. Reasonable thing to do. So I'll have an op-amp and compare it, and then I have to let me erase it, and then I have to fix one current and tune the other current. So here, do you think I can tune both PMOS and NMOS current, or only one can be tuned? Yeah, why not? Why can't I tune PMOS? Yeah, remember that the moment you set the common mode for the first stage, that is setting the gate voltage for the PMOS. So PMOS current is fixed, so you can only play with the NMOS current. Okay. Sorry. And once again, now if I see the second CMFB, so this acts like a first stage. So this goes, connects to the common source, output is taken from the drain and it is put in feedback. So how will this behave like? It's another two-stage OTA. So if I leave it as it is, will it be fine? I should compensate. How will I compensate it now? Let us say use Miller, simplest thing. How will I compensate this now? I mean, for Miller, I should put the capacitor across first stage or second stage? Second stage. So here, where can I put it? So tell me, I mean, NMOS, this is NMOS, right? So that's where I'll go and put the compensation capacitor here. I'll call it CCM2. And again, once again, if you find that the parasitic capacitor here is causing an issue, what can I do? Like this. Just put a small cap there. That will introduce the zero, a faster path to improve your phase margin. So again, anytime you make a Miller op amp like this and you have a resistive feedback, you might find that the capacitance here can cause issues. So this is a simple fix to. Great. So couple of points. Here I am using an op amp here. So it takes in two inputs, one output. What is a candidate you can think of for this? The 5 transistor OTA. How many different variants I can have for the 5 transistor OTA? NMOS input or PMOS input? That's what I meant. So here, what do you think might be a good choice? Why not NMOS? Remember, second stage is output is connected to the gate of an NMOS. So it makes sense that I use a PMOS input for the first stage. So let me actually write it here. So CMFB1 is okay. So now if I look at CMFB2, so you see that this is better off with the PMOS input, right? So the OTA, let us say if I draw it quickly, it will look like this. So this is the output. Sorry. And this output is connected here, so which means having an NMOS input is better. Again, is there something else I should keep in mind for the NMOS transistors, or I'm making a two-stage OTA? So is there some other constraint I should have while sizing the transistors? Equal for? If you don't want to have any systematic offset, what should I do? Current density same for what devices? Yeah, all the NMOS, I'll again mark it with green dots. All of them once again should have the same current density. I mean, anytime you make a multi-stage structure like this, you keep in mind that, you understand what kind of sizing constraints you should have so that you don't unnecessarily introduce offsets. So this is how you will make a two-stage fully differential amplifier, which will be a final project. That is, whatever op amp you are making, I'll ask you to convert to fully differential. Great. And now we have seen with respect to common mode, everything is fine. Let's look at the differential mode picture and see if things are okay, and with that we'll wrap up today. So differential mode is quite easy, just stay with me. So let me erase it. Okay, so for differential mode signal, let us say I apply, what color can I use? Okay, I'll use this itself. Plus VID by 2 and minus VID by 2. Again, for small signals, all the nodes along the line of symmetry they will be 0. So if I start shorting things, this is incrementally short, this is incrementally short, everything here is incrementally short. Same is the case, this is also at small signal ground, this is also at small signal ground. Is that fine? Everything along the line of symmetry. Any node that is sensing the output common mode, that will be at incremental ground. So this is the output common mode, so ground, so this is grounded. So I will try to erase things. I will erase one part of the circuit, so left side I will erase completely. And now look at the op amp here. The output of the op amp is grounded. The inputs of the op amps are also grounded. So the op amp is also not in the picture. So let's see if I can. Yeah. So let me try to draw it neatly here. So here also I will have, let us say, only one part, right? This is grounded. So if I draw this, first I will draw the main transistor, the PMOS and the NMOS. Here is where, say, apply VID by 2 or minus VID by 2, doesn't matter. So this is what I have drawn here for now, right? Now the gate of the PMOS is grounded, that is taken care of. Source is incrementally grounded, taken care of. And I have the second stage, so let me quickly draw the second stage. And I have the compensation. This is the main part. Now let's see what all from the common mode feedback loop will affect you. So from the first stage CMFB, you will have some gate capacitance because you will not use a resistive common mode detector there. That much was clear. So some parasitic capacitance from the first CMFB will come. That will load this. From the second stage CMFB, we have this Miller capacitor, that is, again, this is incrementally ground, by the way. So this capacitor will be connected from the output to ground, so that will come. This is CCM2, and same is the case if I look here, this R and C, it is also connected to the output to ground. So you will have those two components also, finally loading your differential mode picture. So when you are finally designing your differential amplifier, you should take into account the loading introduced by the CMFB also. Only then final performance will be what you expect. Okay. And just to see if you remember things, let's say call this M1, M2, and let us say M3, M4, or let us say M5, M6, and let's say this is CC, RC. For the differential mode circuit, what is the unity gain frequency? What kind of compensation we are using? Miller. So what is the unity gain frequency there? Yeah, but finally what was it equal to? Okay. Yeah, let's say, yeah, beta is, I'm looking at only the unity gain, so GM 1 by, right? Now similarly, remember that you are making a common mode feedback loop. Even the common mode feedback, especially for the second stage you had here, this was another two-stage OTA. Now this loop will have its own omega u. That is the omega u for the common mode signal. I'll call it differential mode. You will have omega u for the common mode signal also. So in the next class we will see what it means for you to have omega u for the common mode. But this is also something you should have in mind. One last point I want to make here is one advantage with this fully differential structure is this. See, let us say you made a normal two-stage OTA which you are designing right now for your project, right? So let me erase this. Remember the first stage in your case will be the 5 transistor OTA. So you'll have, let us say, I'll quickly, if I have to draw this. So you'll have this diode connection. This is your first stage, right? So here in the first stage, along with the pole due to this capacitor, is there an additional pole you have here? Due to which node? You also have this capacitor that will introduce a pole under 0. But if I look at my fully differential case, that is not there, right? Because in a fully differential case, this connection I am not making, so that part is not there. So that is one nice thing, you don't have this additional pole and 0. Hopefully your design will also be easy. Okay. So I'll stop here and we'll continue.